maybe recorded. Let me maybe start by asking if there were any questions about what we've done yesterday. Let me open the chat, actually. No. Okay. So, so today we will do our first field results, right? By which I mean our full rigorous derivation. So, as I said, there are several methods, and I'm going to start with what is probably the simplest one, and which is the approach by McKean. Right. So that's one, and it's a first rigorous derivation. And I'm going to start with a Grumble estimate. All right, so let me again put again the notations and everything, right? So I'm going to consider a general system of that type. Right, and here I am going to assume that S and K are Lipschitz. And actually are even in W1 infinity, so they are uniformly bounded and their derivative is uniformly bounded. Right? And in general, we are going to do this over RD. Now, if you remember a little bit of the discussion of the first day about the models, about the various things, right? We are very, very far from that in many applications. Right? So Colombian interactions are very far away from being Lipschitz. And there's also a whole discussion that we could have about locally Lipschitz versus Lipschitz. And this is actually relatively tricky, so I'm going to bypass that completely by taking globally Lipschitz, which will make my life just so much simpler, and therefore yours as well. Okay, so what do we do here, right? This is a trajectorial approach. So as I explained yesterday, we want to compare with the McLean-Blasov process. All right, and where F is the law, right? F is the law of Exponent. And we are going to do this into several steps. And what we will do first is we will essentially reverse engineer the argument that I had yesterday. Right, the formal argument. So the formal argument was starting from that and then say, well, If the xi are almost independent, then we have a law of large numbers, so we can simplify the discrete sum. And then we observe that we have just n copies of the same process. And so we'll go right in reverse. So the first thing I'll do is I'll create n copies of the x bar. Then I will reverse the law of large number, right? So I will try to replace this nice expression with f by a discrete sum. And then finally, I will compare the resulting system with the system on the xi. Right, so let's describe this. So first step is take n copies of the x bar. Second step is reverse the law of large numbers. And third step, right, is compare with the xi. Right. So this is a rather classical approach that you find a lot in math, right? When we have a nice object, right, and we want to show that it is the limit of an object that we don't know whether it's nice or not. Your first instinct, right, might be to try to put the system of the xi under the form of a limiting system. But very often that's very hard. And so often what happens is you try to do it the other way around, right? You take the limiting system and you put it under the form of the starting system, right? It's what people do in numerics as well. If you have a numerical approximation of something, right? You take the limit and you put it in the numerical algorithm. And so that's pretty much what we're going to try to do here. So I will go step by step. All right, to take n copies here, right, I need something. I need a well-posedness result for the McKean-Blazov process. Which we could have relatively easily, and I'm actually going to postpone that a little bit, okay? To the next section, actually. So here I'm going to assume that we know it is well posed. So what do we need, right? We need a random variable, right? X bar 0. Then you choose a Brownian motion, W, and then you conclude that there exists a unique well-adapted process, right? So adapted with respect to the filtration of the Brownian and all of that. I'm not going to go very much in the technical details here. With low f, right? And this solves this McKean-Blazov process, right? in the sense of Ito's integral. Right, so I'm going to throw under the rug here most of the technical part, right, of the stochastic analysis. I'll just mention for those of you who are a little bit familiar with stochastic differential equations that this is really a notion of strong solution that I'm using here, in the sense that I need to be able to choose myself the Brownian motion. But again, I won't go much further, right? Because otherwise, if you know nothing about stochastic analysis, we would need to have a mini class on that. And again, I don't want to do this. Now, I should say that this is true, and it's actually not very hard once you have the technical tools when case Lipschitz. Right. Any question on this? No? Everyone is good? Seems okay. All right. Perfect. So once we have that, taking n copies is easy. Okay. So with this result, right, for any I, we choose, right, x bar 0, which is xi 0, right? So this is a given random variable. All right, fair enough. And W, the Brownian motion, is equal to Wi, right? And then I have the existence of a solution. An x bar, and now I'm going to put an index I to the x bar because, right, it depends on I, because for different i's, I have a different x I bar. And that x bar I, right, solves the following. Or Lipschitz. And in principle, it's Fi, right? Okay. And now there's a final remark before we move on, is the xi bar 0, right, which is xi 0, they all have the same law. Right? And that law is chosen independently of the Brownian motion. And so a consequence of that, and a consequence of the uniqueness of the X bar I, right, is that all the X bar I have the same law as well. Right. So this law that was Fi, right? I'm going to denote it F, right? Okay. Is that all good for everyone? Yeah. And the final point, again, by uniqueness, right? Since the xi bar 0 are independent, right, and then I solve I pair I independently, then the x bar I are independent as well. And I need the Brownian to be independent, right? Right. Yeah, that is relatively trivial because I'm solving independently for each I, and I have completely independent choices of initial data and Brownian for each I. So there cannot be any correlation at any point. Okay. All right, so this is a little bit of stochastic preparation. After that, the rest is entirely just calculations. But of course, right, doing this rigorously requires some work. So this is not something that could have been done by Newton or even by Blasov, right? We needed the notion of stochastic integral introduced by Ito. We needed the first work on stochastic differential equations that he performed, right? And you needed to understand all of that. Okay, step 2 is reversing the law of large number. Okay, so now we are going to pick a time, any time, right? And we are going to focus on this integral, right? And we want to replace it by a discrete sum. So we are going to focus on that. For a fixed I and a fixed time t. Okay. And I'm going to reproduce the analysis that we had before. So I'm going to define yi, which is this k of yj, sorry, which is this k of xi bar minus x bar j, right? And I'm going to observe, right, that yj is bounded. Okay. And that's because I've assumed that k is bounded. Now, if k is not bounded, but the derivatives are bounded, then you need to propagate moments. It's not very hard. It's just one additional technical step. Okay. And now what I want to do is I want to apply a law of large number. And I want to do that on the right objects. But so rather than using a theorem, because there's going to be conditional expectations, and then you might wonder, well, are conditional expectations justified? You know what's going on, right? Let me do it by hand because this is super simple. So what do I want to do here, right? I want to compare this object with its conditional expectation, knowing xi bar. All right, so I'm going to denote k bar, right? Which is this conditional expectation of k of xi bar minus xj bar, knowing xi bar, right? And again, because xj bar is independent from xi bar, right? This is exactly our convolution. So this is exactly that. Okay. And now I'm going to do the following, right? For I different from j. And now I'm just going to look at the expected value of 1 over n, the sum over j, right, of kxi bar minus xj bar minus k bar, right? And I'm going to take the square, and I'm going to calculate this again, a conditional expectation with respect to xi bar, right? So that's our calculation. Let's call this little e. Yeah, I'm going to call that little ei, right? For future reference, ei square. And so what do I have? Ei square, it's a sum, right? And there are n terms, so the k bar I can put it inside. Okay, and now I have a square of a sum, so I'm going to split that. And I have 1 over n squared, the sum over j equal 1 to n, the sum over k, sorry, L equal 1 to n. And then I have this product, right? Then I have the expectation of k xi bar xj bar, right? Minus k bar dot k of xi bar minus xl bar, right? Minus k bar, knowing xi bar. Okay. So now I'm going to use my yi, right? Yj's, right? As I define them. So this is sum over j and l. And then I have the expected value of yj minus k bar, yl minus k bar, a condition with xi bar. And what I know, right, is that by the definition of yj and the definition of k bar, k bar is actually the conditional expectation of yj knowing xi bar, right? And moreover, the yj, yl, they are independent for j different from l, different from I. Again, knowing xi bar. Depends. X I bar xj bar xl bar yj and yl are independent if I is different from j l, right, and j is different from l. And the consequence is, of course, that here, right, this is equal to 0 if j is different from l, right, and at least one of them is different from I. So in that big sum, right, I don't have much left. Here's 1 over n squared. So I have a 1 over n squared, right? The sum of j equal to L. And then I have the conditional expectation of yj minus k bar square, knowing xi bar, right? So this one, fair enough. And then I also have the case where j and L are both equal to I, right? Which is included into that sum. And remember that I said that the yj are bounded, right? They are bounded pointwise, almost surely. So this is less than 1 over n times the bound on the yj times actually twice the bound because there is also their average, right? So this is 2 over n k L infinity. All right. Easy enough, right? Any question on any of that? No? Okay. So what does that tell us, right? Well, now I can put this into the equation on xi bar, right? So this term, I can replace it. So this implies that dxi bar is equal to s of xi bar dt plus 1 over n, the sum of j equal 1 to n of k of xi bar minus xj bar dt, right? Plus an error, plus 1 over n, the sum of right, the difference. And the difference, right, is what I call EI. So plus, so put so it's minus plus the real thing, right, which is this integral. Right, so I have this thing, and that is what I called EI. Right? Sorry, got to put the expectations here. There's an expectation there. And this is the expectation of EI squared, right? Oops. Let's try to have something that is correct. Right? So yeah, that's what I called EI, right? And all of this is multiplied by dt, and then you have plus sigma and dwi. And what do I know about EI? I know that the conditional expectation of EI square with respect to xi bar is less than 2k infinity divided by n. And there's a square, and this is actually a 4. I should check my notes. All right. Okay. What does it mean to sum? Yeah. So this is the sum of our J and L, but L is equal to J. Let me write this as the sum of your J. Right. And then let's put the Nikitrix function L equal J. Anything else? So again, just stressing, this is the standard law of large number. I just showed you how it was working here, right? Okay. The third point is now compare xi and xi bar. Well, what I'm going to do now is I'm going to subtract. Right? So let's denote a zi, which is xi minus xi bar. And what do I have? I have dzi is equal to, well, s of xi minus s of xi bar dt, right? Because those are the same terms here. This is again the same term, so I'm doing the same. 1 over n, sum over j, k of xi minus xj, minus k of xi bar minus xj bar dt. Plus ei, right? This guy. And this is it. And this is it because the diffusion here, I took a simple case where the diffusion did not depend on the solution itself, right? So those sigma and dwi, they are gone. So we actually have an ODE, right, on the eye. The noise, the Brownian motion, they completely disappear in this simple setting. So I'm going to do a Grumble estimate on the eye. Right? And this is it. So how do I do that? Well, I can take a square, for example, right? And there's no Ito formula. Again, there's no noise here, so I can do whatever I want. There's no stochastic calculus anymore. So for example, let's take a square, right? I like the square because I like having e square, but you know, well, let's not. Let's do the d over dt. Let's take the modulus just to change. Easy. Let's use the Lipschitz bounds now on S and on K. This is gradient S in L infinity, right? Dot the difference between xi bar and xi. Which is di, right? And there's no dt. Put it here. And same thing for the other one. And here we'll get Zj plus Zi plus Ei. Very, very simple. Now I can take expectations if I want, and I can sum over all the i's, right? So let's say that our difference, right, our delta t is, I'm going to choose this particular norm, 1 over n, the sum over I, the full expectation now of the I, right? So this is, of course, that object. Then I take the expectation of this and I sum, right? D over dt of delta t. This is less or equal than what? So I sum over I here, right? And I take the expectation, so I get delta t again. Well, here, so the gradient k goes out of the sum, right? I already have a sum over j of zj, so I already have delta t. After I take on the expectation, I'm averaging again, I'm not changing anything, right? So I have gradient k L infinity delta t. And here zi, so there's no dependence on j, so the sum over j goes away, right? I take the expectation and now I sum over I and I get another delta t. Plus the sum over I of the expectation of ei, right? Okay. What do I know about this, right? This last term. And there's a 1 over n. Well, that's my law of large number, right? So this is less than if I do a Cauchy-Schwarz, right? The expectation of ei square, right? 1/2. And the expectation of ei square is exactly what I had calculated here, right? So I take the square root of this. And you see that then the whole thing is less than twice k in L infinity divided by square root of n. Hence, I have a very simple inequality. Right. Is that good for everybody? Yeah. Now what happens, right, is I can actually yes, okay. Now this is just a Grumble lemma, right? This is just a Grumble estimate. All right, so let's summarize what we have here, and let me write a theorem. Right, so assume that S and K are in W1 infinity of RD. Then we have that the expectation of 1 over n of sum over I of xi minus x bar, right? And this is taken at time t. This is less or equal than an exponential of this. T s infinity plus gradient s infinity plus gradient k infinity times 2 term, right? This remainder plus the initial condition. Okay. So do as a question. Slide 15. Oh yes, there's a gradient of k here. Thank you. And I put it there, and I put it here. Yes. All right. This is it. So this is our first result, right? And so let's discuss it a little bit, because that's quite interesting. Now, first of all, right, for us, because we've assumed that the xi 0 were equal to the xi bar, right, we wouldn't have the second term. But we could, right? In the sense that I wouldn't need to have that the xi 0 is equal to xi bar, right? Here, for us, we took that xi 0 was equal to xi bar 0, okay? But in that case, we do not have the same thing at later time because there is the correction. And remember how I was saying that even if initially the xi are independent, they cannot remain independent, right? This is a manifestation of that. So now, moreover, this is our first result of propagation of chaos, right? And we could formulate it like that. And this is in line with what I've just said, right? Because in this, right, there's nothing that forces me to take xi0 equal to x bar i0, right? As long as I take the xi bar 0 independent, this inequality is correct. In other words, I don't need to take the xi0 independent, strictly speaking. Right, so let's reformulate that as a propagation of chaos result. If the xi0 are almost independent in the sense that there exists, right, xi bar 0 iid such that the difference in this norm, right, the expectation of 1 over n, sum over I of xi0 minus xi bar 0, right, this is small. And this is true for all positive time, right? Because then there exists xi bar that are iid such that the same is true. You see? So we don't propagate independence. Again, we cannot have strict independence. But we do propagate almost independence in that sense. Okay. Again, if there are any questions, please make sure to interrupt. All right, two final remarks, right? We don't have to use that particular norm. Right, so actually, I would get a result on any basically any LP bound, right? With a slightly different rate if p is larger than 2, because then I wouldn't have the right assumption on EI. Right? But we could use this. And I don't need to sum, right, on n, on average. So I could also actually use the following norm. Which is even much stronger. And it's the same calculation. One last remark, however, that is negative concerning this. This is not a good result for a long time. And the problem is the exponential growth, right? So exponential, even if I assume that the initial data at 0, right? This term on its own, right, times 1 over square root of n. This is going to be of order 1, right? If essentially t is large enough with respect to log n. So for our physical applications, right, this is a little bit disappointing because, and even more so for our biological application, right, because unless this gradient k and this gradient s are really small, this is not a very large time. Okay, log n is not a large number, even for n equal 10 to the 20. That's 30, right? Log n for 10 to the 20, something like this. So we're not talking about very, very large time. Now, I really don't want to go in too much of, yeah, what happens if the Lipschitz constant of k is not bounded? I'll mention that, right? But of course, if the Lipschitz constant of k is even large, right, this is a lot worse. But so there is a big question as to whether we can do this sort of propagation of chaos result for a larger time. And maybe if we can do it uniformly in time, right? And you do have some partial results in that regard, especially with noise, with Brownian motions. But This is complicated, even more so than this. I really don't want to go there. All right, and what happens if K is not Lipschitz? Well, you can't use this method at all, right? Especially, again, there could be the question is, can you use it when K is locally Lipschitz? Provided that you control the fact that the trajectories don't go away, yeah, in the right sense, yes, right? But if K is not even locally Lipschitz, which is the case for our applications, right? Coulombian, it's not locally Lipschitz around zero. It's singular at zero. Then this method completely fails. And if you're not Lipschitz, or at least locally Lipschitz, everything I'm going to tell you about this morning, none of it can be used anymore. This is why the mean field limits are still a very active field of research, right? McKean's results are from the 60s. So, you know, almost 60 years after, we are still working on that because the non-Lipschitz case is really complicated. And you'll see a little bit of that tomorrow. Then I hope that will convey the idea that, yes, this is a very simple proof. Any other question? Nope. Okay, so I want to briefly discuss, right, within this. So this is 1.2. What this means, so we have a trajectorial estimate, right? But now you might wonder, okay, so you've shown a bound on the trajectory. Well, I'm not interested in the trajectories. I'm interested in the law. What can you say about the law out of that bound? Okay. So remember that the system here is exchangeable, right? So they all have the same law. Which here I'm going to do a little bit of an abusive notation with respect to yesterday. I'm going to call it Fn. Really, that is the one particle distribution. So actually, it is what I denoted Fn1 in the second lecture. But we're not going to use any other index here, so I'm just going to drop the one. Okay. So the question right here is, can we bound Fn1 minus F, right? Where this is the law of X bar. And so the answer is yes, right? If you control the random variables, you have to control or very low. But I've realized that, and this is not really that hard to do, but it's sometimes not immediately clear for people. So I wanted to do a remark. And this also prepares our next section. So it's useful and shows you which kind of norm you can have on those laws. So what is the idea here? The basic idea, right, is that if you take an expectation of a function of a random variable, then this corresponds to its law, right? Of course, for some function phi, right? Then the expectation of phi of xi, right, is just the integral of phi of x fn t dx, right? And the same thing with phi of x bar I, right? Okay, so let's subtract. All right, so now I have to compare phi of xi and phi of x bar I. Again, that is going to be very, very natural if phi is Lipschitz. Right? So this is less or equal than the gradient of phi in L infinity times the expectation of xi minus x bar I. And you know what? This is true for all I, right? For any I you pick. So it's also true for the average in I. So this is less or equal than gradient phi infinity 1 over n. The expected value of the sum, expected value of xi minus xi bar, which is exactly the quantity that we had. So if I want to control something of f in terms of the quantity I had, right? Well, very obviously, as long as the gradient of phi is going to be bounded, so say less than 1, then that works. So the soup over all phi, right? Such that gradient phi is less than 1, this is going to be nice. Turns out that is the object that I define as the W1 Wasserstein distance or the Rubinstein distance yesterday. So this is a weak distance between Fn and F. Now we could restrict it a little bit further, and then we would get the W minus one norm, right? Just by imposing that phi is also less than 1. This is less than the expectation of. Okay. So the previous theorem also gives you a control on the low immediately. But something I will remark here, right, is this works that way. It doesn't work the other way around, right? So we could have that initially, right, the lows are very close, but that the difference is large. Right? So you get a control on the low, but initially you need more than the low. Initially you need that the xi0 are close to the xi bar 0, and that is not going to be given by the low. All right. Any question? Nope. Okay, then actually I think this is a good time to have a break. So let's do again 15 minutes.
Thank you, Pierre-Emmanuel. Okay, for 15 minutes of break.
So that's 3:35, right?
Perfect.
Okay. See you soon, everyone.
Yeah. So see you in 15 minutes. Yeah.
And Francois, I hope I didn't say too many stupid things on stochastic stuff. But...
No. This was perfect. Thank you. Andrew, this is okay for you?
Yes,
Yes.
it's okay. Yeah.
Okay. Good. All right. So, first questions, if there are any.
Pierre-Emmanuel,
Yep.
please let me just open the micro for everybody who wants to ask audio voice questions, if it is easier. So for a short while, then you may proceed. So if there are any questions and want to ask by voice, please do so. If not, so Pierre-Emmanuel, maybe.
Okay. So
Sarah,
time to go to. Yeah.
Sarah Sadi,
Yes, I have just small question, please.
Sure. Go ahead.
Until now, we have like shown the convergence of, let's say, mean field interaction to some probability measure. And is it like straightforward to introduce this continuity equation or Fokker-Planck equation of this density F?
So that is a perfect question. Okay, in the sense that this is what I'm about to do.
Okay.
Fantastic, thank you. Yeah, so right. So far, there are a few things that I put under the rug, and they are somehow connected, right?
Okay.
And in particular, I didn't say anything about what we could know about the limit.
Okay.
Right, and so there was at the very beginning here, there was this this assumption that there exists a solution, right, to the McKean-Vlasov process. Yeah, and so in particular, there is a solution, there is a law, right?
Yeah, sure.
So this sort of implies that yes, we would have a solution to the limiting McKean-Vlasov equation. But I didn't explain why, I didn't explain how, any of that. Right?
I see.
And this is what we are going to talk about now, still in the Lipschitz case. And so what I will do is I will actually now take a PD point of view, right, and work on the limiting McKean-Vlasov equation.
Okay, thank you.
Any other questions? Okay. So that is our second section. And so I'm going now to ask what we can say, right? On the limiting equation. So the limiting equation, let me write it again, right? Yes. Okay, right, times F. And this is equal to sigma n squared R2 Laplacian x of f. And so this is the Vlasov equation. And I'm going to keep assuming that S and K are Lipschitz here. Okay. If S and K are not Lipschitz, then you can also have difficulty working with this limiting equation. And then it really depends what is actually the structure, what are the assumptions and all that. So you have a whole zoology of results. There is no way that I'm describing them during this class, right? So again, just want to emphasize if S and K are not Lipschitz, then it is actually, right, can be a challenging question to derive solutions, to have good solutions for this equation. Now, one advantage of what we are going to do here, right, is that this will translate into a relatively straightforward estimate on the empirical measure, right? So this actually will end up giving you another way of doing the mean field limit, at least when there's no noise, right? So when sigma n is equal to 0. It would also work with sigma n non-zero. But now we will need to do a little bit of SPD, and I will not want to go into the technical details. All right. So let's start with this, right? And let's start with well-posedness of measure-valued solution. Now, that's sort of the ideal case, right? So our goal is for any probability measure, right? So F0 is going to be a probability measure in RD, right? Show that there exists a unique, right, F T, which now is going to be bounded in time with value in probability measure of RD, right, solving the equation Vlasov, right, the Vlasov equation. This is, in many respects, the ideal situation, right? Because we don't need to ask more than the fact that F is a probability measure, and you know that's perfect, right? Because that's obviously the minimal assumption that we can have here. If F is going to be a low, yes, it is going to be a probability measure. Maybe nothing more, right? So perfect. And the first remark is existence is actually easy. Now, it's easy enough that I'm not going to give the whole proof, right? So I'm just going to sketch it. So the first thing that you're going to to do, for example, is you can regularize S and K so that they are, super smooth, right? And then you'll get existence of a solution to the Vlasov equation for those regularized S and K using a very standard fixed point, right? So take sequences Sn, Kn smooth, right? And find a solution Fn to the Vlasov equation, right? By a fixed point, by a Picard fixed point, right? And I'm not going to show you how to do this. And then you notice that the Vlasov equation, it preserves the mass, right? So Fn is automatically non-negative, right? And d over dt of the integral of Fn, right, t dx, is equal to 0. And this you can justify completely because if you have a smooth solution to a smooth equation, right, you can do whatever you want, so just integrate and then you're happy. So this is true, right? And then this shows that in particular, right, the integral of Fn t dx is equal to 1. And now the set L infinity in time with bounded measure, right? In RD, right? This is the dual of the set L1 in time with functions that are continuous and tend to 0 on RD, right? So it is compact for weak topology, for the weak star topology. Locally compact. For the weak star topology. Right, easy. All right, so that means that you can extract a subsequence. Subsequence. Fn, right, that converge weak star to some F. Right. Now you need to be a little bit more precise. You need to show tightness of Fn, right? So I don't really want to go into that because if you don't know what it is, I don't want to have to explain it. Again, I'm trying to focus on the main parts here. If you know what I'm talking about, showing tightness is actually very easy because K and S are both in L infinity. And what this shows is that F is actually a probability measure, so that the mass is preserved. And then you pass to a limit. In Vlasov equation, and passing to the limit is easy again because Right? The limit of S times Fn obviously converges weak star to S times F, right? Because S is Lipschitz, so Sn converges as a continuous function. Right? Minus S converges in infinity. And actually, it's the same thing for Kn, right? And you can show that Kn converging with Fn, right, actually converges in the same sense. And those are standard convolution estimates, right? Okay, so with a minimum familiarity with PD techniques, existence, you're going to be able to get it, right? Not a big deal. And I'm not going to do it because I don't want to spend an hour filling in all the details that we would need to fill in to actually prove this. So instead, what I'm going to focus on here is on the well-posedness, so on the uniqueness. And by the way, this existence does not even require K or S to be Lipschitz. They only require K or S to be continuous. Uniformly continuous, to be precise. Uniformly continuous and bounded. Hence, we focus here on well-posedness, on uniqueness. Okay, so now I'm going to consider two solutions, right? F and F tilde that are both probability measures, right? And have the same initial data. And I need to show that then F is equal to F tilde. For all positive time. Okay, so in order to do that, I'm going to propagate some norms on F minus F tilde. And again, as before, right, we had the discussion yesterday for the empirical measure, because F and F tilde are only probability measures, so they could have Dirac masses, for example, in them, right? I need to use some weak norm. And not surprisingly, to keep my life as simple as possible, I will use here again the W1 distance, or the Wasserstein or Rubinstein distance. So I am going to want to estimate this thing, right, which is T over dt of the soup gradient phi less than 1 of the integral of phi Tf minus Tf tilde. Okay. And this requires a little bit of care. Okay, because naive idea, right, would be to say, well, let's take a phi, right, a given phi, and then let's do d over dt of this, and then let's integrate by parts the various terms in the Vlasov equation, and that would fail miserably, okay? Because you would integrate by parts, you see that you would lose a derivative with the divergence of x, and basically at that point, you would be dead. So this is really, really not a good idea at all. Okay. And so we need to do something else, right? And I'm going to show you what we need to do on a simpler example, where I'm going to take a linear advection diffusion equation, right? So where the velocity field is going to be given. So basically, I'm going to take k equal to 0, right, in the Vlasov equation, and then I'm going to show to you how we can do the estimate. And then we'll add back the k, and we'll work it out. Okay. So I have a simple case k equal to 0, right? I'm choosing a phi, right? And let's call it phi bar. And we want to control the integral over phi bar, right? F of t dx minus f tilde of t dx, right? Phi bar of x at some t that is strictly positive. And the question is, how do we do that? And how do we do that? Well, and the way we are doing this is we are creating an equation, a dual equation on phi bar. So we are going actually to solve an evolution equation on some phi, put it there, and calculate the d over dt of this, and that is going to be nice. Right. So I'm going to define, right, phi, a solution to the dual equation. So dt phi plus divergence x. That's right. Plus s dot gradient x of phi is equal to minus sigma n square over 2 Laplacian x of phi. And I don't define starting from t equals 0. I don't know phi at t equals 0. I know phi at, so let's call this t0. I know phi at the time t0, so I solve backward in time. Right? So phi at t equal t0 is equal to phi bar. Okay? So you notice that I changed the sign of in front of the Laplacian, right? So I changed the direction of time for the heat kernel, but I'm also solving backward in time. So this is actually equivalent to solving the heat equation in the forward direction, right? So all of this makes sense. Now, I can actually get an equation, a solution to this, right? And I'm going to show you the key estimate there. which is the propagation of the Lipschitz bound on phi. This equation propagates phi in L infinity and gradient phi in L infinity. Now, for phi in L infinity, I have a maximum principle that applies both to the Laplacian and to S gradient x of phi. So actually, phi at any time t, right, t less than t0, in L infinity, this is less than phi bar in L infinity for any t strictly less than t0, right? And this is the standard maximum principle on the heat equation. What about gradient phi of in L infinity? Well, I'm going to differentiate the equation. Okay, so let's take one coordinate alpha, right? And I have to calculate d alpha of phi, right? d phi over dx alpha. So I just have to be careful with the advection term, right? Because s depends on x as well. So when I differentiate, I'm either going to differentiate in x or I'm going to differentiate in phi. Now, if I differentiate in phi, you see that I get exactly the same equation as I had before, right? Except on the alpha phi. But I also have a differential in x. And with a Laplacian, of course, it all goes through. So d alpha phi. And now I'm going to apply my maximum principle again, but I have a problem, right? And the problem is this extra term d alpha s gradient x of phi, which does not satisfy a maximum principle. The others, they do satisfy a maximum principle on d alpha phi for the same reason that the initial equation was satisfying a maximum principle on phi. So here, what I have is d over dt of d alpha phi in L infinity, right? And now this is backwards, right? So forward, I would say d over dt is less or equal, and then backwards, it's d over dt is larger or equal, and then with a minus. Okay. So this is larger or equal than minus the L infinity norm of this d alpha s gradient x phi. Okay. S is Lipschitz, right? So this is larger or equal than the L infinity norm of Laplacian of gradient s, right, times the L infinity norm of gradient phi. And this is true for any alpha, right? So take the soup in alpha, you'll get the L infinity norm of a gradient of phi on the left-hand side. And then I have that, right? Which is another Grumble inequality, the backward in time. And so this implies that gradient phi, right, at any time t before in L infinity, right, this is less or equal an exponential t times the gradient of s in L infinity times the gradient of phi bar, right? So it's t minus t0. T0 minus t gradient s L infinity phi bar in L infinity. But so for any finite time, right, the Lipschitz bound on phi will remain bounded. This shows, by the way, that phi is almost everywhere differentiable, and if phi is almost everywhere differentiable, you have no problem writing down a solution, right? So phi is actually going to be a classical solution for left-hand side, right? Would still have to be careful defining the Laplacian, but everything else would be fine. Okay. Is this calculation all good for everyone? Yep. Okay, seems to be the case. Now we can easily conclude. Oops, sorry. Now let's do d over dt of the integral of phi tx times f t dx. Right. Well, this is the integral of dt phi times f, right, plus phi times dtf. Okay. So I'm just going to introduce the equations. And this is s gradient x phi minus sigma n square over, and this is multiplied by s, and Laplacian phi, this is f. And then I have plus phi, and here I have the same thing with f, so minus divergence of x of sf plus sigma n square over 2 of Laplacian f. And now integrate this by part, right? The integral of phi times minus divergence of x of s phi, right? This is equal to the integral of f s gradient x phi. So this term, right, cancels out that one. And the integral of phi Laplacian f, right, this is equal to the integral of Laplacian phi times f. So that term cancels out that one. Now, so far this is formal, right? I would actually need to work a little bit more on the equation on phi to explain that Laplacian of phi is well defined. This is actually a standard regularization by the heat kernel because the left-hand side here is in L infinity. Right, this thing is in L infinity, so this would give you all that you need, but you know. Again, I'm going to bypass here this slight technical difficulty to make everything rigorous. Again, we will need to take a sequence of approximation phi, pass to the limit into the approximation. That's, I'm not going to do that, okay? But that would be easy. So at least formally, d over dt of the integral of phi times f, right? Times df is equal to 0. And if I did that for f, I can do that for f tilde. I solve the same equation. So what that means, right, is that the integral of phi 0 f0 dx minus f tilde 0 dx, this would be equal to the integral of phi bar f t0 dx minus f tilde t0 dx. Moreover, the term in the left-hand side, right, the one initially, I can control it in terms of the Rubinstein or Wasserstein distance. I just need to make sure that phi 0 has a gradient, right, that is in L infinity less than 1, which, okay, might not be the case because here I have an exponential, so it could be larger than 1, right? But that's okay. Let me just divide by the gradient of phi, right, of phi 0. So this is gradient of phi 0 in L infinity. The integral of phi 0 divided by gradient of phi 0 in L infinity times f0 dx minus f tilde 0 dx. Now that has the right gradient, right? So that is less than gradient phi 0 in L infinity, the sup over all psi with gradient of psi less than 1 of the integral of psi f0 dx minus f tilde 0 dx. And so now if I use this inequality on gradient phi at 0, right? What I get is I get exponential t0 gradient s in L infinity w1 of f0 f tilde 0 provided, right, that gradient phi bar was less than 1. And therefore now I'm using this equality, sorry, right? And now I'm going to take the sup over all phi bar that have gradient less than 1. And I get the following straightforward estimate. right. This is a very important calculation. Again, I just glossed over here. This part of the calculation is formal, right? But everything else is entirely rigorous. There are a few ways of doing this. If there's no diffusion, you can simply use the method of characteristics. With diffusion, you can actually go back to the stochastic formulation of the equation, right? So this is an equivalent of the method of characteristics, but you need to do this well, okay? And if you want to do that at the PD level, you have to introduce this dual equation on here on phi, okay? If you don't introduce this additional equation and you try to do things directly, then it is not going to work. Again, you will not propagate the any sort of weak distance on the solution. Okay, that will fail. So this again is the key calculation here. Okay, the nonlinearity is going to create additional technical difficulties, as you're going to see in 1 minute, but nothing we can't handle once we've understood that how this was working. So any question on that? Yeah, it is actually a standard calculation now. Yep, absolutely. But it is standard now, right? It's the same thing as when I'm discussing section 1. There are a lot of things that become obvious once someone has thought about that, right? And you can use another distance. It's not necessarily as much fun, but it's the same basic principle. So here we could use W minus 1, 1. It would be the same, right? If you want to use other Wasserstein distances, then it's a little bit more painful because you have to define the solution map. So again, if you can use characteristics, it's going to be the same. If you can't use characteristics because you have the diffusion, right, sigma n is not 0, then other Wasserstein distances would be a little bit more painful. Any other question? Okay. Then let's go back to the full case, right? Okay. So I know that if I want to calculate now, we have nonlinear equation on f and f tilde, right? I want to calculate their W1 distance. I need to define a dual equation, okay? And the problem now is I have two versions of the dual equation because the original one is nonlinear, right? So f is advected with s plus k convolved with f, and f tilde is advected with s, the same s, but plus k convolved with f tilde, right? So that's the source of the technical difficulty. Here we are going to trivialize it because I'm just going to write it in another way and throw that under the bus, right? So So I'm going to write that f tilde is actually advected with the same with the same field as f, okay? The same diffusion. And now here I've made a mistake, so I need to correct my mistake, right? So I'm going to add it as a remainder, right? As a correction. Bracket. And now I'm going to so choose any time t0, right? And any phi bar with gradient phi bar in L infinity less or equal than 1, right? And I'm going to define phi on the dual equation corresponding to this advection, right, with S plus K convolved with F. Okay. Now, F is given, right? So this advection here, right? I can call it as bar of X, right? That's something given, right? Depends on time as well. And so as a consequence, right? I have the same estimate as I had before, right? And here there should be, of course, phi at t equal t0 is equal to phi bar. So we have the same estimate as before. Right, so phi of t in L infinity, right, is less than phi bar in L infinity, t less than t0. And gradient phi in L infinity is less than exponential, right, t0 minus t, gradient s bar in L infinity times gradient phi bar, right, in L infinity. Now this is less than 1, right? And gradient s bar in L infinity, right? Look at the definition of S bar, right? It's obviously less than the gradient of S plus the gradient of K convolved with F. And F is a probability measure, right? And K is, gradient K is bounded. So this is actually less. Again, standard convolution estimate, right? This is less than gradient K in L infinity. Right? So we have out of all this, right? Now we have the very simple estimate on gradient phi of t dot. This is less than exponential t0 minus t gradient S in L infinity plus gradient K in L infinity. Okay. Now, phi is the dual equation for F, right? Just as I had defined them before. You see that here I'm pretending that K convolved with F is something given, which it is because F is, we know it, right? And I'm using this as an advection term. So I have a d over dt of the integral of phi df is equal to 0 as before. Easy. But of course, that is not going to be the same for f bar. Now, at the beginning, right, it all works very, very well, but I have this extra term here, right, this extra remainder. So for f bar, right, when I'm taking this d over dt, I will have this extra term. All right, so d over dt, sorry, f tilde, not f bar, d of f tilde, right? This is going to be equal to the integral of phi divergence x of k convolved with f minus f tilde, right, times f tilde. So I can integrate this by part, right? This is minus the integral of f tilde, k convolved with f minus f tilde, right, dot gradient of s. Okay. So how bad is this? Well, let me put absolute values everywhere. This is less or equal, right? F tilde as a probability measure if its integral has value 1, and then I need to take the L infinity bound on everything else, right? So this is less than k convolved with f minus f tilde L infinity gradient s gradient phi, sorry, L infinity. So this is less than that this exponential of t0 minus t, right? Gradient s L infinity plus gradient k L infinity. Okay. Fair enough, right? Well, it's a nonlinear equation, so we have an extra term, right? I pretended that the equation was linear, and there's a price to pay, and the price is here. But it turns out that this is a price that we are happy to pay. because there's a very simple bound on this k convol with f minus f tilde. So let's look at that, right? So this is the integral of k x minus y, right? ft dy minus f tilde t dy. So let's fix x, right? This again looks like a Wasserstein distance, a Rubinstein distance, right? So let me denote phi x, which is k, so phi x of y, which is k of x minus y, right? And this is the integral over phi x of y, ft dy minus f tilde t dy, right? So consequently, k convol with f minus f tilde, right? Again, I'm going to pull out the gradient in y, right, of phi x. And then I will have the integral of phi x y divided by gradient y of phi x, L infinity, f t dy minus f tilde of t dy. The gradient y of phi x, you see, it's just the gradient of k, right? So this is gradient k in L infinity. And this is going to be less than the sup over all a test function psi whose gradient is less than 1 of the integral of psi y d phi minus df minus df tilde. So this is gradient k L infinity w1 of f and f tilde, right, at that time t. Okay, so that I can put it here, right? This I can use it again. And so now what I will have is that d over dt, the integral of phi f minus df minus df tilde, right? This is less than gradient k L infinity w1 of f tilde at time t times this exponential t0 minus t, the gradient s L infinity plus gradient k L infinity. Now let's integrate this between t and between 0 and t0, right? So the integral of f t0 dx minus f tilde t0 dx. This is less or equal than, right, phi bar. The integral of f of phi 0, right, f0 df0 minus df tilde 0 plus the integral between 0 and t of that expression. Let me not write everything here. Now I can take, I can do the same thing for the initial data, right? So this is going to be less than exponential T0, gradient S L infinity plus gradient K L infinity, right? W1 of F0 F tilde 0 plus, again, the same horrible expression here. I take the supremum on phi bar. Of course, still keeping the gradient of phi bar less than 1, we obtain a global inequality in interval form. W1 of F T0 F tilde T0, right? Less or equal an exponential T0 times that. Plus still our super nice expression. And this is something that we can solve by Grumble lemma. And we obtain the following theorem, which is a variance of results from the 70s by Dobrushin and Brown and Hepp. Assume S, K are in W1 infinity. Right. Consider F, F tilde, right, that are in L infinity with value in probability measures, right, and that are both solutions to the Vlasov equation. Then you have the following bound. This is less than W1 of F0 F tilde 0 times the exponential of T times S L infinity plus 2 gradient K in L infinity. So notice that here, right, I had gradient S plus gradient K at this point, right? That's because it's the linear estimate. And in the linear estimate, I see K only once. But it also shows up here, right, in this nonlinear estimate. And so when I do another Grumble inequality out of all of this, I lose a factor 2 on K, right? I see it twice. That's actually quite comparable with the estimate we had on the trajectories, where again, we had gradient S plus twice the gradient of K. Right, so everything fits here. Okay, so this was the huge technical part of the day. Any question? Yeah, don't hesitate. I'll make a few comments in the next sections, but we're mostly, this was the big chunk. No. Yeah, so you can check the papers by Brown and Hepp and Dobrushin, again, late 70s. Another good reference for that is the book by Spohn on many particle systems, because he will, all those calculations, right, that I just showed you, he's doing them. So this trick of having the phi that is time dependent and all that, this is really actually it's the closest to his formulation. So I should write it here. Any other question? Nope. Okay. And let's make a few comments, right, on some of the consequences of this. The mean field limit on the empirical measure. Right? And then for this, I'm going to assume that we don't have diffusion, right? So we now have a system of ODE, right? And I'm going to recall, right, our definition of the empirical measure, which was mu n, which was this 1 over n, sum from I from 1 to n of delta of x minus xi, right? In that case, it is actually a small exercise in the theory of distribution. And you can show, right? Again, K is your Lipschitz, right? K continuous is now again would be the minimum that we need to show this equation. You can show that mu n is an actual solution to the Vlasov equation. All right, so this is a very remarkable algebraic fact, okay? This is not true if you have diffusion. Then you have extra stochastic term, right? Of course, you have a Laplacian, right? But you also have stochastic, non-vanishing stochastic terms. Oui, mon âme, sorry, c'est le handyman. Sorry, we have a repair guy at noon. He's a bit early, but my wife is taking care of it. Now, it turns out that the additional stochastic term, right, you can show that they are vanishing. So you can actually still do that in the case with diffusion. I just don't want to explain it. If I have a solution to the Vlasov equation, I can apply the previous uniqueness, well-posedness result between mu n and the limit f. Now, this is a normal Schur estimate, right? So I'm not taking expectations yet, right? This is true for every realization, almost every realization of the empirical measure. Remember, it's a random measure, even if sigma n is 0, right? Because the initial conditions are random. But almost surely W1 of mu n and f is less or equal than, right, this exponential term. I'm just going to put a constant c here, times W1 of mu n 0 f0. Now you can take expectations. And this is another propagation of chaos. Right. What is the formulation here? Well, the formulation here is that you are chaotic if the expectation of a Wasserstein distance between mu n 0 and f0 is small, right? And then if that is true, then it is true at any later time. Okay. And so propagation of chaos at the level of the empirical measure now can be reformulated as saying that the empirical measure is almost deterministic. Right? So the stochastic variation in the empirical measure have to be small for propagation of chaos to hold in that formulation. Okay. Now, if you compare that with the previous result in propagation of chaos, this seems to be better because there's not this correction in 1 over square root of n. Again, we change formulations, right? So things are not exactly the same. But so something that I want to emphasize here, right, is we actually have corrections there, is just less visible. If f is smooth, right? If it's a smooth function, then the best you can do, the best approximation you can have of a smooth function with a sum of n Dirac mass in dimension d, this is going to behave like 1 over n to the power 1 over d, right? Because the best thing you can do is you have a big box, right? You cut your big box into small boxes, right? And you put the right number of particles in each of the box. And what's the size of a small box that you can have? It's this thing, because you're in dimension d, and you can have at most n particles. So even though it seems it's better, right, because you don't have the 1 over square root of n, in that formulation, it's actually worse as long as n is at least 2, right? Because then this is going to be actually a much larger number than 1 over square root of n. And then everything I have said before still applies. Right, so the problem with the long time and all the discussion we had at the end of section 1, you can redo it here. Okay, and I just want to finish with a, I realize this is 2.2.1, 2.2.2, and I'm not going to say more, right? The McKean-Vlasov process. Okay. So the law of the McKean-Vlasov process automatically has to satisfy the Vlasov equation, right? So F has to solve the Vlasov equation. At least that's the case when K is Lipschitz. Okay. So this gives the existence and uniqueness of the law, right? And so this is another approach to the well-posedness of the McKean-Vlasov process, because once you have the uniqueness and existence of the law, Now, solving the McKean-Blasov process, right? F is known. This is now just a standard SDE. Of course, I have not discussed how you solve standard SDE. So if you don't know that from some other source, this is not super useful. But still, that's another way, right? You can do it directly. You can solve the McKean-Blasov process directly, which I haven't done, but you can do that, right? And then you would get the uniqueness of the Blasov equation as a consequence, right? So this can also work in reverse. All right. I think this is it for today. That's all I wanted to say. So
thank you very much, Pierre-Emmanuel.
Thanks.
Wonderful lecture. Are there any questions?
One question, please.
Yeah.
Yes.
Is there any numerical method to approximate the law F of X bar?
There are plenty of numerical methods to approximate the law. So many that it's actually hard to answer your question. Very roughly speaking, right? First of all, you can discretize the Blasov equation. So all the numerical methods that you have to solve nonlinear PDEs, right? They could apply here. So that's already a lot, right? But you can also solve directly on the McKean-Blasov process, right? You have numerical methods specifically for that. Using Monte Carlo type of method, for example, right? If you solve enough of the instances of the X bar, then you can have a good representation of the law, and then you can fit that back in.
Like a Picard iteration method, like that?
Yes, you can do a PKR iteration method, yes, based on solving the McKean-Blasov process, absolutely.
Some references, please, for the best known methods.
You have lecture notes by Talley, I think, if you're interested on the second part, and François here knows that well as well.
Thanks,
so
thanks a lot.
You can ask him.
Talley is a very good reference. Yes, very good.
Thank you very much.
Any other questions? Okay, then we'll see you all tomorrow.
Thank you again, Pierre-Emmanuel. This was really, 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 really nice. And I think that we all enjoyed your lecture today. Really.
Thank you.
Thank you, Pierre-Emmanuel.
So we will see you tomorrow at the same time, 2 p.m.
Yeah.
Okay.
Okay.
Anything else you would like to say, Abdul?
Only for the notes, for the lecture notes. So when I get them, when Pierre-Emmanuel sent them to me, I will forward. Maybe we will get the two of us. Do you have a Gmail address, François?
Yes, I will do that. I will send it to you. And maybe this is easier that Pierre-Emmanuel send them to me.
Yeah, then I'll send them directly from the tablet, and that will be it.
I will do this. I will send to you the address right now. I will do this.